Okay, there we go. So we're going to talk about this network, and maybe first a small introduction. So in a later class, some of the students have already seen something in this direction. We'll see. I mean, so far we have dealt with, let's say, simple kinetics, but the class is called complex kinetics and non-equilibrium things. So what is that all about? So in most cases, we have a reaction. Let me just start here. And I have A goes to B. And, we teach you, okay, you have all these things like, concentration of A versus time. And, this will be some kind of, first order graph, all fine, right? But it's quite predictable. Predictable can be good. But predictable can also be boring, right? So if you look at many systems in nature, biological systems, there are things like oscillations. A very familiar one to you is, the rhythm of sleeping and waking up is regulated in your body by an oscillating reaction network. Another one that's very interesting is it's called the min system. This is just an introduction, okay? So if you have a cell and the cell needs to divide, how does the cell know where the middle of the cell is? It doesn't have a little ruler where it can just roll out and say where's the middle. So actually, I'm not going to explain this whole system, but there is an oscillator in this system, which is called the min system. And basically, it creates an oscillating pattern in this cell, which concentrates at the poles. And then based on this, the cell knows where the center of the cell is. So then it can divide, and you have two cells. So cell division is a very famous oscillator. Then, we also have to, 1 second, participants. 1 second, there's some noise on the background. Okay, there we go. Okay, that's better. So oscillations are important. This is a spatiotemporal oscillation, which maybe we'll get to at the end of this class, but that's a bit too complicated to start. So we're going to start with something simpler, and that's oscillations in time. So how can we get, let's say, something more interesting than just this, but let's say we want to get something that does this in time. For example, a damped oscillation or sustained oscillation. So I'll explain you in more detail about this field. This is basically coming from the field of what's called nonlinear dynamics. Okay, nonlinear dynamics, which is a whole field. And let's say the best known oscillator is called the Belousov-Zhabotinsky reaction, which we'll get to in a later class. But today I'm just going to use this as a hopefully interesting example of what kind of complexity you can get in a quite simple chemical reaction network. So the one you see here on the left only has a relatively few species and relatively few chemical rate constants. And this is actually, it's not the smallest equation that can show oscillations, but it's the smallest, let's say, chemically realistic system that can show oscillations. So don't worry about all this oscillation hop terminology, because we're going to come back to that later. But we're just going to look at this in the same way that we looked at all the other kinetics equations that we've seen before. So we're going to start by writing the rate equations for each of these species. Then we're going to do some steady state approximation. Okay. We're going to solve this. Then we're going to take all these equations, we're going to code it in Spyder, solve it, plot it, and then probably we need a break. And then after the break, we'll move this code to Jupyter Notebook, which is also in Anaconda, which will allow you to play with the variables in a very easy and natural way. And so basically, if you can do this, you can code up any chemical reaction network that you will see in your career. Okay, so let's get started with this. So basically, we will start again like normal, and we'll start by writing the rate equations. So let me stop this for a moment so you see it better. Okay, so let's start with the species x, right? So I'm going to write dx dt. If you're lazy, you can just write x dot. That means the derivative in time. Okay, so x dot. And we're going to look, okay, where are the species x? So I color them in red. So you can see that in reaction 1, right, which is labeled with K1, x is being consumed. So we can say, okay, we have x and a give a reaction to give 2x, right? So if I would maybe write these reactions out in a simpler way, I can say x or a plus x gives 2x. Maybe it's simpler to see like that. Okay, so with K1, right? So let's look at the rates, what that does. So I will have the disappearance of x, so minus K1 times a times x. Okay, but I have also the formation of x, right? So I have plus 2 times K1 times a times x, right? X is being consumed, but it's also being produced. Okay, let's see, where else is x involved? You can also see at the bottom, x goes to z with K4, right? So x is disappearing, so we say minus K4 times x. Okay, so that's important. And where else? So at the top you can see that x plus y goes to a plus y with K2. Okay, so that gives x is being consumed, so minus K2 times x times y. Okay, so we can see that here, okay, we have 2k1 ax, and here we have minus k1 ax, so that drops out, right? So this is just k1 times a times x minus k4 times x minus k2 times x times y. Okay, and we can write it, well, we can write it a bit shorter. I don't know if we really care at this point, but okay, let's just say we're going to say k1 times a minus k4 times x. It's not the shortest, but okay, we'll just stick to this writing. Okay, so that's for x. Then for y, dy dt is y dot, right? So let's see, where's y being consumed? So you can see it in the same reaction. So with K2, well, actually with K2, it's interesting, right? Let's just write it. But K2, 1y is being consumed, and also 1y is being produced, right? So if we write that, let's just do it for fun, it would be minus K2 times xy, but also plus K2 times xy, right? That's that top right branch. So that cancels out, so it turns out to be 0. So I'm going to just not write it down, save some space. Okay, let's see where else is y being consumed in K3. So minus, well, minus K3 times y. And y is being produced from z. So z goes to y with K5. So we have plus K5 times z. Okay, that one was easy. Let's do that for z. dz dt is z dot equals, okay, let's look at z in purple, right? It's being produced from x with rate x4 or k4. So we have k4 times x, and it's being consumed because it's converted to y with k5. So we have minus k5 times z. Okay, last one, dA dt is a dot. Okay, so let's see. A is being produced from y with rate k3. So we have k3 times y. It's being also produced in reaction 2. So we have plus k2 times x times y. And it's being consumed by reaction 1. So we have minus k1 times a times x. And so one case we're going to consider here is that there's a little 0 if you see in the network, A0. And that means in this case that we're going to use a chemostat. It's a bit weird word, but chemostat. It's like thermostat. You know, you have a thermostat in your house. The function of a thermostat is to keep the same temperature. The function of a chemostat is to keep the same concentration of a certain species. And you would think, oh, that's a weird machine, but that actually is quite commonly used as to maintain pH of a reaction. So you can use a chemostat to, for example, keep a system that is not buffered, but you want to maintain a constant pH, you can use a chemostat. Okay, so since we're using a chemostat, that rate is 0 because there's no change in the concentration of A because the chemostat is always keeping that concentration the same. Okay, right. So let's look at the steady state. I don't need this. This was just a repetition of some of the parts of the network. Steady state. Okay, so let's say this network on average stays at steady state. So I'm going to say x dot equals y dot equals z dot equals 0. So I'm just saying that the average, okay, this should have averages. So often people write like this. So it means that the average concentration over a given time will remain constant in the steady state. That's just an approximation we're going to make. Okay, so let's see how we can solve that. So from, let's say, the second equation, let me look. Yes, so from here, right, we can see that Z, oops, there we go, Z equals K3 over K5 times Y. And from the third line, okay, should have maybe drawn this jump. Okay, from this one, we can see that K4 over K5 times X, this is true. Okay, so from these two, we're going to say Y equals K5 over K3 times K4 over K5 times X. So kill is K4 over K3 times X. Okay, that's nice. Let's look from the first line, right? So from this one. Let me just rewrite it. So K1 times A minus K4 times X equals K2 times X. Now I'm substituting K4 over K3 times X. Okay, so from that, we can do K2 times K4 over K3 times X squared minus K1 times A0. Oh, sorry, I wasn't writing the 0 yet. A minus K4 times X equals 0. And then I always solve it using the ABC formula, which is really not the most convenient in this case, because you can solve it easier. But okay, let's just go for the hell of it. Right, so there will be a solution. So I'm just using the ABC formula, right? Minus B plus or minus B squared minus 4AC over 2A. Okay, now you can see that I'm not very good at this. A minus K4 plus square root over K1 times A minus K4 squared minus 4 times C, well, that's 0, so that's 0, easy up, 2 times K2, K4 over K3. And that turns out to be K1 times A minus K4 times K3 over K2, K4. So that's one solution. The other one, of course, is X2 is 0. Okay, so it's 0 or that. Then for Y, say solution 1 will be K4 over K3 times X is K1 times A minus K4 over K2. Okay, or of course Y2 is 0. And Z1 is K4 over K5 times X. 1 is K1 times A minus K4 times K3 over K2, K5, or Z is 0. These are all averages, right? Time averages. Okay, so from the steady state, we can see that there are two solutions. Let me color this. Okay, so solution 1, we have x1, y1, z1, just this, and this. And the more boring one, solution 2, would be all 0. Okay, so that seems to indicate that there is a situation where not all the concentrations are 0, because that would be extremely boring, where we can have some interesting behavior, which is non-zero, which we can solve using this steady state approximation. But what we don't see from this steady state approximation is that this solution 1 can be quite interesting. So you'll see I will put this paper on Moodle, and it's a long mathematical paper. So you see that there are more analytical things you can do to analyze this network with stability analysis, and you can go all crazy. But we are not going to do that because we're not mathematicians. So we're going to find a practical way of solving this. Okay, so I hope you copied these equations, right? Because we're going to need them now that we're going to code up this network in Spyder. Does anyone have a question about this first part on how to look at the network, how to write down the rate equations, and then doing this steady state approximation? Okay. Good. Okay, so let me go out of this. And I go to Spyder. Let me share screen. Spyder. Okay, so if you could start up Spyder, it would be great. And we'll start with coding this up. Okay. Here we go. So as usual, we're going to maybe save this file first. I'm going to call it HOPF 2021. Okay, so first we have to import a number of toolboxes like we saw in the past two classes. So we're going to import NumPy as NP. Okay. We need the ODE int, the integrator for the ordinary differential equations. So we're going to do from SciPy dot integrate import ODE int. Okay. So NumPy is for the arrays and matrices. SciPy, we use ODE int for the numerical integration of the ordinary differential equations. We're also going to make some plots. So we're going to do import matplotlib .pyplot as PLT. And we're going to do some fancy 3D plots. So we're going to do from MPL underscore toolkits dot mplot 3D import axes 3D. Make sure you write axis, the A with the capital and the D with the capital, otherwise it's not going to work. Okay, so these are all the libraries I need. Just call it libraries. There we go. So we're going to define our rate constants. So as you saw in the network, we have 5 rate constants. Rate constants. K1 for the moment, we'll set it to 0.2 to start, and all the other ones, K2, we're going to set it to 1. K3 is 1, K4 is 1, and K5 is 1. Okay, now comes the important point. So define your model. Okay, so I'm going to use def to define. I'm going to call my model very originally model. And it has 2 inputs. It has an array of concentrations and time. And I put a colon, very important, otherwise it doesn't recognize it. Enter. Okay, so the first thing I'm going to do, which is a bit weird, is that all the concentrations are going to be stored in an array. So when I want to use specific values in my model, I first have to, let's say, unpack them from this quantity C, which is an array. You'll see how that goes. So I'm going to define my species, right? So I have X, it's my first species, is, and I'm going to just say C0. So that means in the array that we're going to call C, the first value, so 0, because that's the first in Python, again, remember the index doesn't start at 1, but at 0. I'm going to say that is my concentration of X. This will start making sense in a bit, okay? So Y is the same, but the second value. Z is C, oops, 2. And A is C3. Okay, so I'm just taking my input concentration C and I'm splitting it into 4 variables so I can use them in my equations. So let's start with the first rate equation, which I'm going to call dx dt. And it's the one we analytically solved, like by looking to the network. K1 times A minus K4 times X minus K2 times X times Y. dy dt is minus K3 times Y plus K5 times Z. And for Z, we wrote dz dt K4 times X minus K5 times Z. dA dt, we said that one is 0, okay? Because we said A is in a chemostat, so its concentration does not change. Okay, and I'm going to pack all of these concentrations into a variable that I call C out. So concentration out is dx dt, dy dt, dz dt, dA dt. Okay, and then return C out. Okay, so let's look at what we're doing, right? So the input is an array which has 4 concentrations. Then it calculates the new concentrations. and it gives us an output, these new concentrations of this individual step, right? And the step, it's it's handled by the integrator, so we don't have to worry about that. So we just have to say, okay, put some initial concentrations in. This will give you the initial concentrations. Then calculate for this very small time step dt what are the new concentrations, and give them back out in the model. And then that's what the solver ODE int needs to compute the solution. Okay, so now we have to define the initial conditions, or no, it's the initial concentrations. Okay, so make sure you're all the way to the left with your cursor, and we're going to call that C0. So concentration at time 0 is, let's say 5, 5, 5, whatever. What did I pick? 5, 5, 5, 4. Okay, so those are my initial conditions, right? Where if you look at this array, right, so this would be X, Y, Z, and A, right? These things go into your model, split into X, Y, Z, calculate the new concentration after this delta T, and give it back out to the model, which then goes in the solver. Okay, we'll see how that goes. So we have to define for which time points we want to solve. Define time points. So we're going to use T equals NP linspace. Remember, so this is a linear array with a starting value, a stopping value, and a number of points. So we're going to solve from time 0 to time 200 with 5,000 steps. So I've defined my time, and now solve coupled ODEs, right? Ordinary differential equations. Okay, so I'm going to call that C int. So concentration integrated is ODE int model C0, oops, 0, not O, time. That's it. So C int will then be an array where you have all the concentrations versus time. Okay, maybe we can just run this and see what it looks like. Run. Okay, it runs. In my case, it doesn't give any errors. So that is good. Let me look in my variable explorer. So I have my initial concentration, which has 4 numbers in it, 5, 5, 5, 4, which is this line here, right? It's just the definition. I have my my rate constants, K1, 2, 3, 4, 5, which this one is a float because it's 0.2, so it automatically picks float. Here it took integer because it's a whole number. Doesn't really matter in this case. Time is an array with 5,000 numbers in it, which starts at 0 and goes to 200, okay, with 5,000 points. And I have my C int, which is, if you double click that, okay, you can see it, but you'll see it on your screen. You see 4 columns that start at 5, 5, 5, 4, and then decrease, except for the one of A, which is the last one, stays constant at 4, because it's chemostated, right? So we said dA dt is 0, so the initial concentration of A just stays at 4 forever. Okay, that's nice. Let's try to plot these results. So plt.plot. So I'm going to put on the x-axis time. And I'm going to use my results, so cint, which are the integrated values. And I'm going to open brackets because I'm going to plot the concentrations of x. So I'm going to say colon, which means all rows. 0 means first column. So all rows of the first column of cint, which if you open it in your variable explorer, you can see it's 4 columns by 5,000 rows. And I'm going to plot it as a blue line and label is x, like that. Okay, so make a plot of x-axis time of all the x values, make it a blue line and put a label x. Okay, so I'm going to copy this line and paste it 3 more times because we have 4 species, X, Y, Z, and A. Okay, so I Control V, Control V, Control V. Now I just increase this index, right? 1, 2, and 3. And I'm going to say red, black, dashed line, and green dashed line. And I update the labels Y, Z, and A. Okay, so I'm just repeating the same plot there. And I'm going to label the axis. So PLT Y label concentration and PLT dot X label time. Oops, sorry about that. And I'm going to put the legend, PLT dot legend location equals best. So it just puts it wherever it fits. And maybe PLT show. Okay, that is just a simple, let's say, simple 2D plot of the results. Okay, we're going to do some fancier plot as well. 3D plot of the results. Okay, so in this case, we're going to make a new figure, fig equals PLT figure, because we want to open a second figure, and I call it fig equals that, because for some actions, you want to assign more complicated things to a figure, so you need to kind of have a variable name for that figure. Okay, so we'll see how that goes. X is fig dot add subplot 111 projection is 3D. And you're like, how am I supposed to know all this nonsense, you know? So I also didn't, right? So you go online, people have made a library, they've often put examples. So it's basically a matter of using Google and copy pasting things that people write online. Okay, so I'm going to do, I'm going to again plot all the concentrations, right? So the first column, cint the second column, cint the third column. So these are again the concentration of X, Y, and Z. A we don't care because it's constant, and C is red markers, and marker, comma, marker is circles. Okay, there we go. X, set X label, X. Again, going to copy it 3 times, up, up, set Y label, Y, and set Z label, Z. BLT dot show. Okay, so what does this do? It makes another figure, and it plots a scatter plot in 3 dimensions, where on one axis you have concentration int 0, which is X, right, which is this one. C int all rows second column is Y, and C int colon comma 2, so the third column, it's Z. And it's a 3D plot, so we cannot plot 4 variables, right? So we're plotting X versus Y versus Z. And we're going to do it with red open markers. And then we just put the X label, X, Y, Z, and then PLT show. Okay, that was a whole long story. So let's run this and see what happens. And so I have to share this figure. So now you should see this figure. So figure 1, which is the simple 2-dimensional plot. You see that it starts at 5, 5, 5 for X, Y, and Z. And concentration of A, which is this green dashed line, it's 4, it stays constant. And in this case, very boringly, X, Y, and Z just decrease and go to 0. So let's see what it looks like in the phase space. This is called the phase space. So you can see concentration of X, Y, and Z. We start here at 5, 5, 5 for X, Y, Z. And then the solution goes there and it goes plop to 0. And that's it. Pretty boring. Okay. But now let's go back to Spyder and we change a little bit these constants. So let's change for K1. Everyone is able to see a plot in their version, I hope. If not, let me know. So we're going to set this to 1.94. Don't ask me why. We're going to get to that point. I change this to 1.94. I press run. I run my solution. Oh, that's actually not a good solution. Sorry about that. Why not? K1 1.94. Let's see what I did here. Okay, so we have a problem. Let's lower it a bit. 1.8. No, still not. There's some numerical problem. Okay. Interesting. Okay, this is where the misery starts. Typically, so that must mean we have either a mistake somewhere. Let me see in the equations, K1 times A minus K4 times, that looks okay. That looks okay. Looks okay. The X, Y, Z. See out, yeah, 554. Let me see what I had here, 554, 0.2. I don't get why we have something different. Bim, bim, bim. excess work done on this call. ODE int warning. Interesting. Okay, I don't know why that's doing that. 554. 554. That looks good. Oh, wait. We're taking the time way too long. So it explodes. Okay, so let's set the time to 0 to 25. Rerun it. Yes. Okay, so apparently that became unstable after some time. But now that we set the time to 25, there was a typo from my side. We can see in the 2D plot, resume share, why not? 1 second. Okay, so in the plot, you can see that in the two-dimensional plot, we see now that we start still at 554, but you see that the concentrations of X, Y, and Z are increasing and they're starting to show some oscillations. And if we look at that in the three-dimensional plot, we can see that that makes these very nice loops in the phase space, right? So we start here at this beginning of this curly point, and we go around, and we go larger and larger and larger. And what we'll see later in another class is that it goes to what's called a limit cycle. So limit cycle is a shape in the three-dimensional space. So this is called the phase space. It's nothing fancy. It's just the concentration of X, concentration of Y, and the concentration of Z. So what's interesting is this is not a time plot, right? Because time 0 starts at this point here, and then in time it goes around. But what's interesting when you have an oscillator is that in this phase space you can get the appearance of a well-defined shape. So this looks pretty nice in 3D. And at some point when you get sustained oscillations, the solution will keep going around on a certain path, which would be, sorry, I don't know why it keeps stopping this share. Sorry. There you go. So again, so we start at this time 0 here, so at concentration 555, and then the solution goes in time over this shape, and it goes around, 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 around. So when this shape looks identical for many, many cycles, for many, many oscillations, you call it a limit cycle. We'll get back to that. So now you're probably wondering, okay, that looks like a bit of abracadabra to me. How can I actually find, where my solutions can be interesting? So for that, we're going to use another tool, but we're going to do a break before that. So are there any questions? Sorry, let me open the chat. Okay. So yeah, so other people found for the other conditions also oscillations. So it's indeed true that you can change the initial concentrations, you can change the K values, you can change the time, and under certain conditions, it will oscillate. And so this model is a pretty good oscillator, so it's not that difficult to find these solutions. But it can be quite challenging to find what's called the oscillating window, or any space in your variable space where something interesting happens.
Sorry, I have a stupid question, but still, how can I actually move my 3D plots, rotate them just because it's fixed?
Yeah, so okay, so maybe probably in your version, your plot appears in your console. Does it appear, let's say, in this text here? Or does it pop out like a separate plot?
It's separate.
It's separate. So in my version, at least, if you just click on the figure and drag it around with your mouse, it should move.
No,
Maybe.
it doesn't.
No.
Okay, so just I need to
Okay.
update my version.
So let me see. 1 second. Let me just switch to my desk. Oh, I'm sorry. It could be in your Python settings. So let me share. So if you are in Python and you go to preferences, yeah, sorry, I'm on Mac, so I'm not entirely sure if that will work for you. But in the IPython console in graphics, I have this set to automatic, but you can try these other ones, Qt5, Qt4. You have to restart your Spyder and then try again. But sometimes some of these plots don't allow, for example, the interactive, to have the plot interactive and turn it around. So I think
Okay, we'll try. Thank you.
It could be that, but I'm not 100%. So we're going to use another tool that is in the Anaconda Studio, which I'll show you now. So share my desktop. Okay, there we go. So Anaconda. There you go. So in the Anaconda Navigator, you have another number of tools. So all of them are very interesting, but for the moment, so we use Spyder so far, right? Which is this MATLAB-like, graphical environment. And another very interesting thing is this Jupyter notebook. And so it says it's an interactive notebook environment. So it's actually nice. You can type text, you can write equations, but you can also compute inside the file. So this is rapidly becoming among physical chemists, chemical physicists in general, a nice tool to share results, because you can write your story, and in the inline you can have your computation. Okay, so let's click launch. You click launch, it opens some terminal thing, and you see that now you are, in my case, I'm in Google Chrome, but you're basically, you're in a web browser, and it says something like localhost, blah, 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 which means this thing is now, it's running on your computer, but it's using the, let's say, the graphical user interface that is just HTML based. And so I put on Moodle a file. So if you go to your Moodle and on the course, sorry, let me switch to your version, student. Okay, so you should see on the Kinetics page in class 567, I put this Jupyter Notebook empty template. So you can download this file. Okay, so it looks like this. I'm going to download that. Okay, so save it. It has this IPython notebook IPYNB extension. Okay, so you can copy that code and save it somewhere on your hard drive. And so we're going to open that file. So I'll give you a second maybe to download it or find it. So go to the Moodle page, class 567, click the bottom file, Jupyter Notebook empty template, class 7, download that file. And then you go to your browser in Jupyter, and then basically you navigate to where you saved your file. So I'm going to do, in my case, it's here, calculation scripts, OD models. And I'm going to open this empty template.
I can't download it. It's just the script on my screen and nothing more.
Yeah, so if that happens, I think you can right-click, maybe right-click Save Link As, and then save it as a file. It's a bit annoying. Yeah.
Thank you.
So on my computer, it also sometimes does that. Like it just shows like this kind of HTML code, which is abracadabra. So right-click, or you can also, once you have the abracadabra screen, you can also right-click Save As, and then you can save it as a file as well. Okay, yeah, that's a bit annoying. So we go back to this, and so let's investigate a little bit what's going on in Jupyter. So maybe just as a side note, I'm just going to open a new notebook, Python 3, just to show you what it normally looks like when you open a new file. So it looks, you have a kind of command line where it says in, so that's input, the same as in Spyder. But the difference is that basically every box, you can consider it as a separate entity. So if I do 1 + 1 and I press enter, nothing happens because I have to run this box. So if I do run, it will run just this box. And if I say 2 + 3, enter, nothing happens. If I do shift enter on Mac, it will run that box. Anyway, so it's just a number of inputs, outputs, just like in the version of Spyder that you've seen before. But actually, it is quite useful. I will show you why. Okay, so let me go back to that file that we opened. And it just has a comment. Okay, so it's made 1st of February today. And I just, again, I'm going to import all these libraries that I needed in my Spyder script. And okay, and I'm just initializing some stuff. And this is the reference to this paper if you want to read all the details. Okay, so what are we going to do? And so this looks a little bit difficult, but it's really not that difficult if you understand the concept. So we're going to run this box, which is going to import all the toolboxes, all the libraries. And then we have this second box here. And the second box basically says PLT figure, so make a new figure. And we're going to make a function that is going to be called update plot. And as an input, we are just going to change K1 and the concentration of A. Okay, and I already kind of prepared your space here. So we're going to indent our entire Spyder code in here. And then we're going to run this basically in a loop. So this function actually loops whatever code you put in between here. And we're going to make some sliders that you'll see how that works. And then it's going to update that plot with the new values and recalculate. So as soon as you hit run, well, we don't have code yet, but we're going to put the code here. But then when you run this whole thing, it will make an interactive plot where it's updating the solution every time you move the slider. Okay, what does that mean? Let's go to Spyder. Okay, and I'm going to copy the libraries I already have, so I don't need those anymore. But I'm just going to do everything from here. And I'm going to copy it all the way to the first figure. Let's see if that works. So Control-C or Command-C on Mac and switch to the other thing. And where I put this thing, insert code here. So delete that and just go Control-V. You paste your entire thing. And okay, unfortunately, it didn't do the indentation. So we have to make sure that everything is at the same level as this first line. Otherwise, it's not going to be contained in that function. So I don't know if there's an easy way to do that. Maybe view, let me see. Maybe you just press tab. Let me just try. I press tab. Oh yeah, okay. So you select the whole text, and if it's not at the right indentation, you press tab once and it will shift everything to the right to make sure that it's all on this same vertical line. Let me just draw a line so you can see what I mean. So it has to be all on this line, okay? Otherwise it's not going to work because we have to stay in this function here, right? And if we don't do that, then it's going to run the code in a different way. Okay, clear all drawings. Okay, so let's see what that looks like. Okay, let's press. We go to the first box and we do run, and then run the second box, and it works. Yay. I hope it works for you. Okay, let me just leave it here for a second. So again, this whole piece, I just copy pasted from Spyder, where I already, verified that my equations are correct and that everything is okay. And end of basic code. Here I go, the indentation goes back. So here I'm saying widgets. So what is this widget? So you see below the plot, there's now two sliders, one with K1 and one with A0. And you see that because we took the same values, I guess, of K1. Oh, wait. We have to do one thing because now it's just running my code from Spyder, but it's not going to do anything with the sliders. Right? No, the sliders don't work. Why? Because we actually don't give any input. Right? So what I have to do is I have to remove K1 here. Plop. Because that is going to be, let's say K1 is defined by the slider. So we don't want to override K1 after putting it as an input here. And concentration of A, it's actually constant. So we're going to put just A in the initial conditions. So we have 555 A because I'm feeding as an input here A. And so I want my solver to use that in the calculation. Okay, let's run this box again. Run. Okay, now I have a different solution. K1 is 0.26 and A0 is 1. So you can drag this solution, and there's another problem. It's not deleting the old plot. So we have to do something. I always forget what that is. I'm just going to look in my notes. So BLT, yeah, so we need this BLT.CLF, so clear the plot. Okay, so let's go and put that just in front of where I start the plotting. I put this BLT.CLF, save this, because that's going to clear the plot instead of put 100 plots on top of each other. So press again, run. Okay, and now if I try my slider, it should do something. Yeah, so if I move concentration A, you see that this green line moves up and down, right? So it's running your calculation in real time. So every time you change the slider, it runs the code and it gives you the solution.
Sorry, it doesn't.
Yeah. Sorry? It doesn't?
Sorry, but for me it doesn't. I don't know why.
Okay. So what I did, I went a bit fast. So I here was before K1, right? K1 is whatever, something. This one I removed. Okay. Oops. I'll just do it like this. And I put A here in the initial concentrations.
Yes.
So if your indentation is right, it should, when you click, maybe you have to run everything again. So you can just select the first box and do run, and then do run again. And then it should stay active and run. No, it doesn't. Oh yeah.
No, it doesn't. Okay. I will try to figure
the joys of technical issues. Let me just put, I can put in 1 second, I can put the complete file on Moodle. Just give me 1 second. Just go to Moodle. Return. Edit. 1 second. So I will put add file. Jupyter working, at least on my version. Okay, I'll upload this one. Second. Okay, so I now put on Moodle in class 567. I put at the bottom Jupyter working. So if you could try to download that file and see if that one works. Does not work for me neither. Or A follows the same line as X. Okay, so if A follows the same line as X, then there's a problem for sure. Okay, so maybe we can you can all download this new file I put on Moodle. This one should run. Let me check. Yeah, so this one runs. Okay, so it's running on your version. Great. So try to play. No, the new one also not?
No.
Okay, interesting. Yeah, so it seems that there maybe your code, maybe you can hit this like round thing here, which is restart kernel. Okay, so just click restart. It will reset everything.
Mm-hmm.
And then you can do try again, run, and then run. Sorry, so put your cursor in the first box and then run, then try.
Nope.
Interesting. Yeah.
Okay, if
so,
I'm the one, I'll figure it out later.
Yeah, so try a bit, and otherwise after the class I can try to help the people one-on-one that are not managing. Okay, but basically, okay, this was maybe a lot of coding for today, but the nice thing about these sliders is if you have a system where you don't know where to find your oscillations, then the sliders are a kind of very nice visual way to quickly find a solution. So that, well, that could be interesting if you're exploring a model that actually has difficult oscillations. So it's a very engineering approach, you know. Okay, so it's a very low-tech solution. You know, we don't need to know a lot of mathematics because Spyder and Jupyter Notebook are basically solving our model. We didn't even integrate it analytically, like we just write the model and compute it. So that's the strength of Jupyter and of Spyder. So that was basically what I wanted to show you for today. So any questions other than the one that your script is not working, we can stay a bit on the line after that. Does anyone have any questions about, you know, how to go from the analytical equations, writing the rate equations, to the ordinary differential equations, then coding them up, solving them in Spyder, right? Defining rate constants, defining the model, defining initial concentration, time, integrating, and then plotting. And then the slider thing is just a little bonus to more quickly explore your solutions. Any questions?